Hello everyone. In this video, I'm going to go over some practice questions for the test. So the first set of questions are about passwords. Using the 26 lowercase letters, the 26 uppercase letters, and the 10 digits, a 6-character password is to be chosen. For passwords, you can repeat characters and order matters. How many possible passwords are there that begin with 3 numbers? So since we are selecting characters in order, we can break this down into a series of 6 decisions, 1 decision for each password, for each character in the password. So the first decision, what character goes first, the second decision, what character goes second, and so on. So I'm going to lay out a little roadmap for the answer here, where I'm going to multiply together 6 numbers, and the numbers I'm going to multiply together are the number of options that I have for each character in this password. So how many options do I have for the first character? Well, in this question, it has to begin with a number. So for that, we have the 10 digits. So our number of options for the first character is 10. 0 through 9 are the options. And then for these first 3 characters, they all have to be a number or a digit. So I have 10 options for each of them. And it stays at 10. It does not go down to 9 or 10 because I am allowed to repeat characters. By the way, I have to apologize. I'm kind of stuffed up, so if my voice sounds really nasally, that is why. Now, after that, I'm allowed to use any character, so I can use letters as well. So 26 lowercase, 26 uppercase, that's 52 letters in total, plus 10 digits, that's 62 options if I'm allowed to do any character. So I'm going to put 62 in these last 3 places here. So I'm very free for my last 3 characters, but my first 3 characters had to be numbers. Okay, now what is the probability that a randomly chosen password begins with 3 numbers? So for this question, I'm going to do the probability formula. So on top, I'm going to put number of ways to do the event, and on the bottom, number of ways to do the experiment. So the event is choosing a password that begins with 3 numbers, and then the experiment is just choosing a random password. Okay, so on the top, I'm going to put number ways to get a password that starts with 3 numbers, and then on the bottom, number of ways to get any password. Okay, so on the top, I'm going to have my answer from the last question, 10, 10, 10, 62, 62, 62. By the way, you can abbreviate that as 10 to the third times 62 to the third if you want to. So that's going to go on the top. Now what's going to go on the bottom? I need to put the number of ways to get just any password. So without any particular properties. So just looking back at the initial description up here, a 6-character password, and these are the letters and the digits that I'm allowed to use. So I should have 62 choices for any character, any of those 6 characters. So this is going to be 62 to the 6 on the bottom. And if you want to, you could simplify this because this is basically on the top here, you've got 3 10s multiplied together, oops, the 10, and then 3 62s all multiplied together. So if you forgot your rules of like exponents for canceling exponents, I'm just explaining how you could do this cancellation even if you forgot how to use the exponents. You could cancel these 3 62s right here with these 3 down here if you want to. You don't have to. I don't typically ask anyone to simplify answers in my classes because it's not an arithmetic class. But if you wanted to do this, you could. Okay, the next one, what is the probability that a randomly chosen password does not begin with 3 numbers? Now, the event is not beginning with 3 numbers. So I want to put on top number of ways to get a password. Oh, you know what? Actually, I'm sorry. I want to do a different formula for this question. I was about to show you a less efficient way to do it. I think what I actually want to do here is the probability formula for not. I was about to try to do the counting formula for not. So So it's this formula right here. The probability that an event does not happen is 1 minus the probability that it does happen. So what I want to do actually is probability that the password does not start with 3 nums is going to be 1 minus the probability that it does start with 3 numbers. Okay. So this is going to be 1 minus whatever I got in the last question. So I can put this form of the answer or this form of the answer, whichever one you like better is fine. And again, I think you can probably hear how stuffed up I am. I apologize. Okay. How many passwords end with 2 letters? Now we're back to counting. It's not probability, it's just counting. So we're going to multiply together some numbers or maybe add some numbers. So we're going to do this the same way we did the first one. Passwords, the order of selection of the characters matters. So I can break this into 6 decisions, just which character goes first, which character goes second, which character goes third, and I multiply together the number of options I have for each decision. So how many end with 2 letters? All right, well, if I don't care about these first 4 characters, then I can do any of the 62 characters that I have available. So upper and lowercase letters and the 10 digits. And then for the last 2, it says letters, but it doesn't say upper or lowercase. So there's 52 letters if we count upper and lowercase as different, which they are different for passwords. I think that should have been implied here. I think that it's case sensitive. All right, so that's ending with 2 letters. Now, what is the probability that a randomly chosen password ends with 2 letters? So the same way that we did up here, to make this into a probability, we're going to put number of ways to get a password ends with 2 letters. So that is the event. So the number of outcomes that belong to the event go on top. And then the number of ways to do the experiment in general. Number of ways to get any old password goes on the bottom. So this is going to be the same denominator that we had before, 62 to the 6th. And then the top is going to be the thing we did on the last problem, which is right here. Okay, so this is 62 to the 4th times 52 squared. All right, so that's what goes on the top. And then on the bottom is going to be 62 to the 6th. And if you want to, you can cancel out. You would cancel 4 multiplied copies of 62, so that would leave you with 52 on the top. And then 62 twice on the bottom. Okay, how many possible passwords begin with 3 numbers and end with 2 letters? It's a little bit harder, but it's not much harder than number 4. So what's the difference between this and number 4 actually? Is that I just need to change these beginning numbers. So if I begin with 3 numbers, that means I have a digit for my first 3 characters. There's 10 digits, 0 through 9. So I have 10 options for each of those starting 3 characters. And then letters, I have 52 options for each of my last 2 characters. And then this 4th character right here, can do any character, so 62. What is the probability that a randomly chosen password begins with 3 numbers and ends with 2 letters? So I'm just taking my answer from number 6 and I'm just turning it into a probability, which amounts to just putting it over 62 to the 6th again. Okay, so this is going to be number of ways to get a password that begins with 3 nums and ends with 2 letters. And then on the bottom, just number of ways to get any password. Okay, so on the bottom is 62 to the 6, and on the top is this beautiful number here. Oops. Doesn't like it when I get line breaks in the clipboard. Okay, so we can cancel 1 multiplied copy of 62, but the rest of it's not going to cancel. So what are we going to be left with? 3 10s, 2 52s, 5 62s, I think. Or you can just leave it like this big, beautiful answer here. That's fine as well. It's fine with me anyway. maybe not some other math teachers. What is the probability that a randomly chosen password begins with 3 numbers or ends with 2 letters? So here you have to take note of the word or. We're going to use our probability formula for or, which is up here. Probability that one thing or another thing happens is probability of the first event plus probability of the second event, and then you have to subtract the probability that both events happen, and that is so that you don't double count the outcomes that are overlapping, that belong to both events. Because if you just add them together, you would have counted anything that was in both groups twice. Okay, so you have to subtract this to account for the overlap. Now we do have these answers from the previous questions here. So what we're going to do is probability of begin, let's just abbreviate it like this, begin with 3 nums or end with 2 lets is going to be probability of beginning with 3 nums plus probability of ending with 2 lets minus probability of both, so beginning with 3 nums and ending with 2 letters. Okay, and we should have all 3 of these numbers from previous questions. So the probability of beginning with 3 numbers, I think was up here. Yeah, right here. I'll take the small version of it, but any version is fine. Okay, and then the probability of ending with 2 letters is right here. All right. And the probability of both of those things happening, that was number 7 here. Okay. Actually, if I hadn't done any canceling, then they would have the same denominator. Oh well. All right. So this is the answer, and you can check this in a calculator, or you can leave it like this. Last one in this section, what is the probability that a randomly chosen password does not end with 2 letters? So for this, we can use the not formula for probability again. It's this one. Probability that an event does not happen is is 1 or 100% minus the probability that it does happen. That's what the 1 means. That's 100%. Okay, so probability not ending with 2 letters is 1 minus probability of ending with 2 letters. So we're going to do 1 minus, and then we're going to grab that answer from wherever it was. Probability, I think it's this one. Yep. Okay, and there it is. All right, so that's it for that section. And let's move on to the company, the employees section. So we have a company with 50 employees, and they have the following properties. We have 2 departments, research and development, R&D, and marketing and sales, M&S. And we have 2 locations, on site or from home. So we've got 30 that work on site, 20 work from home, 24 in R&D, 26 in marketing and sales. So we have them all broken down into these different individual categories. And now we're going to do the experiment of selecting one person at random from the company. Determine whether the event works on site and is in marketing and sales are independent. Okay, so there's 3 ways you can check for independence of events, whichever one is most convenient to you. These are the 3 equations. Whichever one you decide to check, you calculate the left side, calculate the right side, check if they're equal or not. So if they are equal, the events are independent. If they're not equal, the events are not independent. And so that is how you check. So let's just go with the first one, I guess, unless something goes wrong. So we're going to compare the probability of one of the events to what its probability would be if we knew that the other event had happened or was true. Okay. So we're going to do P of A versus P of A given B. Okay, so we will check P of A, check if that equals P of A given B. Okay, so it's up to you what you think A and B are. I'm just going to do works on site for A and then marketing and sales for B. So we're going to calculate probability works on site, and then we're going to compare that to probability of works on site given marketing and sales. So this is still just for the event of drawing one person. So the second one here, you interpret it as meaning what's the probability that the person you picked works on site, given that they are in marketing and sales? So these events apply to the same person. Okay, let's do the first part first. Probability that the person works on site, I'm just picking one random person from the company, from the whole company, so it's out of 50. And then works on site, there are 30 people that work on site. So 30 out of 50, or 3/5. Now, what if I know that they are in marketing and sales? So the given condition applies to both the numerator and the denominator of your fraction. So now what I want to do is number that work on site, number who work on site, given that they are in marketing and sales. And then on the bottom, number of total employees, but still given they're in marketing and sales. I think I spelled employees wrong. Okay, so you're narrowing down both pools, the top pool and the bottom pool. All right, so the number who work on site, given they're in marketing and sales, is 10. And then the number of total employees, given that they're in marketing and sales, is 26. So this is 5 out of 13 if you want to reduce it. You can throw this in a calculator if you're not sure, but these are not the same. I've reduced them as much as possible, and they don't reduce to each other, so these are not the same number. Okay, so these are not equal to each other, so the events are not independent. Okay, now let's look at works from home and R&D. Guessing they're probably not going to be independent either. Most likely, if one was not independent, they're probably all not independent, but we can check anyway. Let's just try checking a different way, just like for fun, just to show you that it can be done different ways. Let's check. There's the third way. This is the third way you can check. It's a little different from the first two. Okay, so we will check. Okay, so I'm just going to calculate both sides. The probability of both events, so works from home and in R&D. So we'll compare that to probability of works from home times probability of in R&D. So no givens on this way of checking. We just multiply those two probabilities together. And if those events were independent, then that would actually give us the probability of both of them happening. Okay, the probability of both events in the same one person that we're going to select. So works from home and R&D, that is these 4 people right here. And it's out of the total pool of 50. So this is 4 out of 50. See if I cancel a 2 from the top and the bottom, 2 out of 25. Now if I multiply these two probabilities together, works from home is 20 people out of the 50 total. 8 out of 50. Or 2/5, and then R&D is 24 out of the 50 total. I do not think that these are going to turn into the same number. So this would be 2/5, and then let's see, if I cancel a 2, 12 over 20. Yeah, I don't think so. There's no more cancellation I can do because this is 5 on the bottom and then 5 times 5, and there's no 5s on the top. Yeah, so this turns into 24 over 125, and there's no more cancellation that can happen. You could throw these in a calculator if you're not sure whether they're the same or not, but I'm convinced they're not the same. Okay, not equal, so the events are not dependent, independent. Okay. Now let's look at the task of selecting a 4-person committee. So not just one person, but a 4-person committee. So we're going to do this without repetition because you can't fill more than one seat on a committee with one person, right? So no repetition. But the order of selection will not matter. No one's going to have any special roles, so we don't care what order we pick them in. In how many ways can the committee be chosen if there must be 2 people from each department? So what you're going to do here is break this into a series of 2 decisions. First decision, which is pick 2 people from R&D. Second decision, pick 2 people from marketing and sales. So how many ways are there to do each of these 2 things? So from R&D, put the big number on top, little number on the bottom. We have 24 people in R&D, and we want 2 of them. So 24, choose 2. This notation stands for the answer to the question of how many ways are there to select 2 people in no particular order from 24 people. And this one is going to be 26, choose 2. And what do we do with these 2 answers here? How do we combine them? We multiply them together, because we have to make both of these decisions to get our full committee. So your final answer here is multiply these 2 together. Don't just like put them kind of nearby each other or like put a comma between them. They are being multiplied. So if you write these right next to each other, that's multiplication, or you could put like a dot between them like that to show me you're multiplying them. Okay. What is the probability that a randomly chosen committee has 2 people from each department? So we're going to use the answer we just calculated as part of this, but not the whole thing. So on the top, we want to put number of ways to make a committee with 2 from each department. And on the bottom, number of ways to just make any committee. But it's still a 4-person committee, so the number of ways to perform the experiment under discussion, which is making a 4-person committee. So any 4-person committee. Okay, so the answer we just calculated in the last problem is going to go on the top. And the thing that's going to go on the bottom is the number of ways to just select any 4 people from the company. So that's going to be 50, choose 4, like that. Okay. In how many ways can the committee be chosen if all 4 people must be from the same department? So this is a little tricky because it doesn't tell you what department. So you have to do some interpretation. You have to interpret this as how many ways to get 4 people from R&D or 4 people from marketing and sales. So you interpret it as an or between 2 events, and then calculate how many ways there are to do each of these separately. Okay. So let's see, there's 24 people in R&D, 26 in marketing and sales. And we already know how to calculate these 2 things separately. So there are 24 choose 4 ways to get a committee, all from R&D. And there are 26 choose 4 ways to get a committee, all from marketing and sales. But how do you combine these? So you're just going to add them together. And you don't need to worry about any overlap because it's not possible to do both things. Now, did I actually explicitly put that formula in the formulas here? If you're watching this in a future semester, I might have put it on here, but this time around, I don't think I actually did. So this question might be like slightly unfair. Basically, the counting formula is the same as the probability formula. If you want to know the number of ways that one event or another event can happen, you add together the number of ways the first event can happen and the number of ways the second event can happen, and then you subtract the number of ways that can both happen at the same time in order to not double count them. Okay, so for this one, yeah, in all, there are, so we're going to just add these. And we don't need to subtract the number of ways to do both events because it is not actually possible to do both events. Either, and no need to subtract the number of ways to do both things because that is impossible. These are mutually exclusive events. Okay, number 15. What is the probability that a randomly chosen committee has all 4 people from the same department? So here we could actually use that probability formula I was just showing you. Probability of getting a committee from R&D plus probability of getting a committee all from marketing and sales minus probability of both, which the minus part will be 0 because you cannot do both things. Okay, so this will be probability of all 4 from R&D plus probability of all 4 from marketing and sales minus probability of all 4 from R&D and all 4 from marketing and sales, which this last part is going to be 0 because that's impossible. Okay, so probability of getting all 4 from R&D is the number of ways to choose all 4 from R&D over the number of ways to choose any 4 people for the committee from the whole company. And then this next part is going to be the same way, but using 26 instead of 24. And then there's actually nothing to subtract here because these are mutually exclusive events. Okay, so you can leave that last part off if you want. What is the probability that a randomly chosen committee does not have all 4 people from the same department? Okay, so basically this is the same as 15. I've just put the words does not in front of it to make it the opposite. So when you want the probability of the opposite of an event happening, you just do 1 minus the probability of that event. So this is going to be probability of not all 4 from the same department. That's going to be 1 minus probability that they are all 4 from the same department. Okay, so that's just 1 minus whatever we got on the last question here. Make sure you subtract that whole thing, whatever it was, that big beautiful number, put it all in parentheses to make sure it all gets subtracted and not just part of it. So if you leave the parentheses off around this part, you would only be subtracting this first part, and then you would be adding this second part. All right, so we need to put the whole thing in parentheses there. All right, last part for the employees. What is the probability that a randomly chosen committee has all 4 people from the same department or 2 people from each department? All right, got an OR event, so I'm just going to approach an OR event the same way as I always do. So this will be probability that all 4 are from the same department plus probability of getting 2 from each department. And then I'm going to do minus probability of both things happening. But I already know, actually, this last thing here, this is impossible, so that's going to be 0. I'm not able to choose all 4 from one department and half from each department. I can't do that on the same committee. I could do that if I had 8 people, but we're not making an 8-person committee. We're making a 4-person committee. So the experiment does not allow me to do both of those events at the same time. Okay, so this is basically it's the mutually exclusive formula down here. When events are mutually exclusive, you don't need to worry about subtracting the overlap. Or another way to think of it is that the overlap would be 0. Okay, so back to this. I already have these answers from the previous questions. So the answer to number 15, that's the first part. And then the answer to, where was it? Yeah, the answer to number 13, that's the second part. And then you can write minus 0 or you can just leave that off. This is the whole answer here. All right, let's go to the next part with cards. I'm going to put that in the next video on this playlist here, so that should be coming up.